Okay, so we are trying to prove this theorem. That suppose V in projective space is an expanding point, an invariant expanding point. Let nu k converge to nu, and eta k v nu stationary for each k. Suppose eta k's are non-atomic, have no atoms, has no atoms near V, then eta of V is 0 for any accumulation point eta of the sequence. And in order to prove this, we fixed we took small neighborhood U0 of V. Last time I was assuming that eta k has no atoms at all, but in fact the only thing I need is that it doesn't have atoms near V. So this is a small neighborhood such that eta k has no atoms in U0. And the other condition, so the proof is going to be by contradiction. Assume eta of V is positive, and we're going to get to a contradiction. And if eta V is positive, then we can choose the neighborhood such that the measure of this atom is bigger than 9 over 10, the measure of U0. Then what we did last time was using that V is expanding, we can find U1 contained in U0 sufficiently small so that the expanding behavior of V is still just by continuity still true in this neighborhood. And this is expressed by the following fact. This is expressed by the fact that the integral of 1 over distance a n x v1 a n x v2 integral averaged over x, so this is to a power delta. So in this neighborhood, V is expanding. V is expanding, and so in the neighborhood we still have by continuity a certain expanding behavior, which means that on average, an of x v1, an of x v2 are further away than v1, v2 in average. And as a consequence, when I integrate 1 over the distance, this is smaller than the distance, the 1 over the distance between v1 and v2. I should put brackets here, but I'm starting to get tired of the brackets. And then even multiplied by a factor smaller than 1. Okay. And this is for every v1 and v2 in this smaller neighborhood. Okay. Of course, if there are no atoms in U0, then there are no atoms in U1 as well. Then the statement is the following. The main step in proving this theorem is the following proposition. There exists a constant C such that for every k, large, and any symmetric self-coupling CK of eta k restricted to U1 we have the following fact, that the energy of eta k restricted to U1 is less or equal than 1 minus C delta the energy of CK plus some constants. Okay? And the important thing here is that this constant is independent of K. Okay? So I already started proving this last time without stating it. Maybe that was a little bit confusing. What this is saying is that you give me any self-coupling of this measure, and I'm able to get some other, an optimal self-coupling. I'm able to get another whose energy is much smaller than this one. By much smaller, I mean at most a factor with a multiple with factor smaller than 1 than this, multiplied by this, plus a constant. Okay? So I can always improve energy by a factor smaller than 1, and the only price I have to pay for that is fixed constant. So if you assume this, I can finish the proof of the theorem, and then we will continue with proving that fact over there. So how do you prove? So assuming this proposition, let's deduce the theorem. So how do we do that? Of course, we can take the CK in the statement to be delta optimal for eta k. In other words, I may start from the very beginning with a coupling whose energy is equal to the energy of eta k. And if I do that, then this formula becomes this inequality becomes that the energy of eta k is less than 1 minus c delta itself plus a constant, a fixed constant. And this implies that the energy, we just simplify this inequality, is smaller than c divided by c delta. So the whole point is that in this way, this kind of inequality implies that the energy of all my stationary measures near in the neighborhood of the expanding point, they all have an energy which is uniformly bounded. Okay? So this is finite. Now, eta is an accumulation point for the sequence up to taking some subsequence or restricting it to a subsequence. We may assume that eta k converges to k, to eta. And then I have to be slightly careful here. So let me do this. Try not to lie. So let us call, so we may suppose that eta is the limit of the eta k's, limit in the weak star topology. And let us call eta hat the limit of limit, or again accumulation point, of eta k restricted to u1. Well, morally speaking, if eta k converges to eta, its restriction to u1 should converge to the restriction of eta to u1. But that's not true in general. The weak star topology doesn't imply that. Okay? For example, if I have absolutely continuous invariant measures corresponding to densities like this, these are the eta k's, then eta k converges to the Dirac mass at point 0 in weak star topology. But of course, eta k restricted to 0 does not converge to the Dirac mass at 0 restricted to 0. This is the zero measure, and this is a probability. Okay, so the problem is that as a weak star topology allows the mass of the measure to escape through the boundary. So, in general, it's not true that this eta hat is the same thing as eta. However, one thing is true, and that is that for open sets, and I'm assuming that U1 is an open set, for open sets we have that eta restricted to U1 is smaller than eta hat, which is smaller than eta restricted to U1 bar, the closure. Okay. So you see, it's almost the same. For example, if the boundary of U1 has zero measure, then this side is the same thing as this side. And so, indeed, in that case, eta hat is the limit, the weak star limit of eta k restricted to U1. So what do we have? First of all, we have by semi-continuity of the energy by lower semi-continuity of the energy, we have that the energy of eta is less or equal, eta hat, is less or equal than the lim, even the lim inf of the energies of eta k restricted to U1. And since all of these energies have this bound, it is smaller than C over C delta. Okay? So that implies that the energy of eta hat is finite, implies, of course, that eta hat has no atom with mass bigger or than 1/2 the total mass of eta hat. Okay? So, on the other hand, this is the first observation. On the other hand, eta U1 is less or equal than eta hat, then less or equal than eta restricted to U1 bar. And so, first of all, eta hat of V, because of this inequality, eta hat of V is less or equal than eta of V. Eta hat of U1 is less or equal than eta of U1, which is less or equal than eta U1 bar, which is less or equal than eta of U0, because I chose U1 here, I chose U1 contained in U1 bar contained in U0, sufficiently small neighborhood. And this was bigger than 9/10 of eta of U0. So the conclusion here is that eta of V is bigger than 9/10 eta of eta hat of U1, which is 9/10 of the total mass of eta. Okay, so we have a contradiction. These two are in contradiction. Of course, it's easier to see what is going on if you just pretend that eta hat is the restriction of eta to U1, and then the last part is essentially immediate. Okay. So the miracle is that the expanding behavior of V gives us this, and that's what I have to explain next, gives us this inequality, and this inequality implies that the energies of all these measures are uniformly bounded. And measures that are uniformly bounded cannot accumulate, cannot generate atoms as we go to the limits. Because as you build up to produce atoms, this forces the energy to go up. Because you're putting a lot of mass in a small region of space, so the electrons are very close, and that forces the energy to go up. Okay. Okay. So all that is left to do is to prove this proposition and then to explain how we remove this assumption. So, to prove the proposition, the first step is very natural. That's what I did last time. I'm going to repeat it here. So let's draw a picture where the expanding point V is here, and this is the neighborhood U1. This is the product. So you start with CK, any symmetric self-coupling. Self-coupling of eta k restricted to U1. So that's a measure in the product whose projection here is the restriction of eta to U1, and whose projection here is also the restriction of eta to U1. So the first step is to let the dynamics help you. So let CK twiddle be the image of CK under diagonal push forward by A and X. The diagonal push forward is the map here in this product that sends V1, V2 to AN X V1, AN X V2. So when you do this, you are taking the image of this region by AN of X, you're taking the image of this region by N of X. So the image that you get looks like this. Here, this represents AN of X of U1. And I'm drawing this region bigger because we know that on average V is expanding. So for most values of X, the image of U1 is bigger than U1 itself. V is fixed, and it's a repeller. But of course, for some values of X, the image would be smaller. That depends on X. On average, it will be bigger. The measure CK is here, and when I do the push forward, I get a measure CK twiddle that is here. Okay, in formal terms, formally, to say that CK is the image is to say that the integral of a function C V1 V2 with respect to CK twiddle is equal to the image of C ANX V1 ANX V2 integrated with respect to the original measure CK for any bounded measurable function C from, say, P times P to R. Okay, just push forward by diagonal. The fact, and this is still something that I did last time, the fact that this property that the integral of 1 over the distance ANX V1, ANX V2, d mu of x is less or equal than 1 minus c delta times 1 over the distance from V1 to V2, the delta. This property implies, so this property is saying that on average the distances between points in U1 get expanded, and as I already observed, that implies that the energy of ck twiddle is less or equal than 1 minus c delta, the energy of ck. Okay, so near an expanding point, the dynamics itself increases distances, and so the dynamics decreases the energy. But we are not done yet because ck twiddle is not a self-coupling of eta k restricted to U1. And we would be very happy if that were true, because if that was a self-coupling of eta k less than U1, it would give me this inequality without the constant. Right? If I could find one self-coupling of eta k restricted to U1, if this was such a self-coupling, then I would have this inequality without this constant. How do I know that it's not a coupling? Well, first of all, because there's no reason why it should be a coupling of eta k restricted to U1, but it's easy to see in the picture. Where is supported ck? Most likely on a bigger domain. Ck is the I'm sorry, I should have written here integrated with respect to x. So I think in order to calculate ck twiddle, I have to take the image under all these transformations here for different values of x, and then I integrate with respect to x. So most likely this is supported on a larger domain. So one thing that we could do is to restrict to this domain here, to this square. So maybe, who knows, we get lucky, maybe ck twiddle restricted to U1 times U1 is a self-coupling of eta k restricted to U1. That would be fantastic, because when you restrict C, the energy can only decrease. You are integrating in a smaller domain, the energy can only decrease, and so this inequality remains true for the restriction of U1 times U1. Well, but that's not true. That's not true. So to see if that is true, let eta k1 be the projection of ck twiddle restricted to U1 times U1. So the question is this projection the same thing as eta k restricted to U1? That's what I'm asking here. I'm repeating the same question. To say that this measure is a self-coupling of eta k restricted to U1 is to say that when I project it, I get eta k restricted to U1. Okay. Now, this is not an obvious. The answer is not obvious. You have to look into what is going on, but the answer is the following lemma. The lemma says that the answer is no. That this measure here is bigger than this one, and the lemma tells you what the difference is. So the lemma says eta k restricted to U1 is equal to eta k1 plus ik plus ok. The nice thing about this lemma is that it tells us exactly what the difference is. The reason these measures are denoted I and O is because one corresponds to a motion inside the domain and the other towards the inside, and the other one is towards the outside. But I have to where ik is the image of let's see, the image of eta k restricted to U1 complements under A and X restricted to U1. So let me try to explain this in a picture. So in IK, what we are doing is that we are looking at the measure that is outside. The measure that is outside, we look at its push forward under AN of X. In some cases, in most cases, AN of X expands. So what is outside of U1 remains outside. But sometimes we have the opposite behavior. For some values of X, AN may actually contract here. And so part of this measure under iteration may come inside. And that is the part that we are interested in. So if you want a formula, what that means is that the integral of phi V1 with respect to IK is with respect to IK is the integral of phi composed phi of AN of X V1 with respect to integrated with respect to eta k V1 maybe I should use different letters here. U and W. Integrated with respect to W. And integrated with respect to mu to x. And here the integral is on the complement of U1. So W on the complement of U1. Yeah. For any function from U1 to R. So that's what IK is. But the good way to think of it, the right way to think of it is there's some measure of eta k that lies outside of U1. For some values of x, not all, not even most, but for some parts of the complement of U1 complement go inside. They carry some mass, and that's what IK is. That's what it's called. Why I'm using this notation. The measure that moves inside. Mass that moves inside from U1C to U1. Now I have to explain what is OK. That corresponds to the opposite motion. Measure that was here and somehow moved outside. And so this is equal to the projection on the first coordinate of CK twiddle restricted to U1 times U1C. So in the picture, that's this. The part of CK twiddle that lies here. Okay, that's mass that used to be here, and when I did the push forward, moved outside. Why only this and not the whole thing? Well, because I'm only considering the projection on U1. Okay. Of course, there's more mass that goes outside, but I'm only taking the projection here. Okay, so I think I'm not going to prove that lemma because it's essentially a calculation, and since if one is not familiar with these things, the calculations are mostly incomprehensible. And once you get familiar, they become trivial. Well, maybe not trivial, but easy. So the point is that I'm trying to get this relation if I could pretend that the push forward, diagonal push forward, restricted to U1 times U1 is a self-coupling of eta k, I would have this inequality. But it turns out that it is not. It's too small. And so there are two additional terms. Now the lemma also says two things. The lemma also says that the total mass of OK is smaller than the total mass of IK. So the measure that goes outside is actually a little bit smaller than the measure that goes inside. The reason is essentially because I'm only considering this part that goes outside. There's a little extra that I don't count because I don't care. On U1 is the only part that affects the projection on U1 is this one. And the other fact in the lemma is that IK is also small. The lim sup of IK, the total norm, is less than 1/10 of the mass of the atom. And the reason is also, I mean, this, if you think it's not so surprising, this. We are in a region where, I already erased it, where the atom is responsible for more than 90% of the mass. So this accumulates essentially all the mass. So the amount of mass that can come inside, remember this is a fixed point. If you are here under iteration, you can come here, but you cannot get very, very close because this is a fixed point. And your matrices are bounded because all these probability distributions are supported on the compact set. So all these are motions that take place near the boundary of U1. Going inside and going outside is something that affects, it's a boundary effect. Okay? And near the boundary of U1, the mass is very small compared with the atom because the atom takes care of 90% of everything, and that 90% doesn't move. It's stuck here. Okay, so the statements are not obvious when you look at them in the first time, but if you think these are kind of reasonable. The reason for this inequality is that, in fact, we are only looking at some part of what was thrown out. Otherwise, it would be equal. And this is this boundary effect that I described. Okay, so now we have a problem, and the problem is this. Now the problem is this. We have here a measure, eta k1, here. And for eta k1, we have a very nice self-coupling, ck twiddle restricted to U1 times U1. This is a self-coupling of eta k1, symmetric. All my self-couplings at this point are symmetric because, by definition, with energy which is pretty small, less or equal than the energy of the complete ck twiddle, and so less or equal than 1 minus c delta e delta of ck. Okay? As I said, if you restrict your measure, that can only decrease the energy, and so this inequality remains true. Okay? But the problem is that that's not the measure that we want to look at. We want to look at this measure. Okay? And we want to find a self-coupling for this perturbation of eta k1. We want to find a self-coupling that that has an energy that's not too much bigger than this one. So in fact, in view of the statement, I want to find a self-coupling for this measure here, for this measure, which is just eta k restricted to u1. We want to find a self-coupling that whose energy is at most this plus a constant. So since I already have the self-coupling for the small measure, for the bigger measure, I'm going to look for a bigger self-coupling. Okay, so I'm going to try to construct that self-coupling Ck bar, okay, self-coupling for eta k restricted to 1 to u1. The obvious thing is to start with Ck twiddle restricted to e1 times u1 and to add something. Right? Of course, that's dangerous, because when you add, you increase the energy. And I'm giving myself the right to increase the energy only by constants. So how can I guarantee that? I already gave you the secret, at least the strategy, last time. I'm going to add terms all of them supported far away from the diagonal. If I put these terms far away from the diagonal, avoiding some neighborhood of the diagonal, then they will contribute bounded amounts to the energy, and that will be done. Okay? So this is the clever part of the strategy. Try to find extra terms here in such a way that when you project the sum, you get eta k1 coming from this, and these two terms give you ik. These extra terms give you ik plus ok, but all of the extra terms are supported somewhere far away from the diagonal. Okay. Well, once you have this strategy, you sit with a bunch of pieces of paper and a pen, or preferably a pencil, and you start playing with what you can do. I don't think there's any systematic way of doing this. You just start trying, and after some time of trying, you may come up with the following solution. There's, of course, more than one solution. But you may come up with the following solution. Fix neighborhoods so u1 containing U2, containing U3, containing U4, containing U5 of V, such that the idea is that each neighborhood is much smaller than the preceding one, such that a n x of U1 contains U2 for every x, for almost every x. U2 contains the closure of U3. U3 contains the closure of U4. U4 contains ANX of U5 for mu almost every x. Okay, so remember, V is fixed. And then you just take U1, take a much smaller neighborhood so that whoever starts in U1 will, what is this? So whoever is in U2, its pre-image under ANX will be in U1. Then you take U3 much smaller, U4 much smaller, and then U5 even smaller. In fact, in our first version of the argument, we had 10 of these neighborhoods. Then we simplified to 5. And finally, you take U5 such that any point that is in U5 under iteration cannot leave U4. It remains in U4. And then, so I have to draw these neighborhoods here. I have to make U1 bigger. Then you have U2, you have U3, U4, U5, 5, 3, 2, 1. And then now I can tell you what the extra terms are. I mean, how one possible choice. If you ask me how you get to find these terms, well, you just try. You know what you want. You want them to be bounded, to be supported far away from the diagonal, and you want them to project these extra terms. You want them to project to ik plus ok. So one possible choice is minus zeta k divided by eta k4 ck twiddle u4 times u4 plus 1 over ik ok restricted to u3 times ik plus ik times ok restricted to u3 plus 1 over eta k4 zeta k times eta k4 plus eta k4 times zeta k, where zeta k is 1 minus OK restricted to U3 divided by IK times IK plus OK U3 complement, and eta k4 is the projection of ck twiddle restricted to U4 times U4 to the first coordinate. Once you have this expression, it's just verify that they satisfy what you want, and you are happy. And as I told you, I don't think there's a very heuristic motivation for these formulas in particular. Let me just show that they do have the kind of properties that we want. First of all, here we have a difference. And when we have a difference, we have to be worried because we can only work with positive measures. But that's okay, because this quotient is smaller than 1, because the total mass of OK is smaller than the total mass of IK, and if you restrict, that remains true. So zeta k is a positive measure. Okay? Observations. And I'm going to say where it is supported. So this is the first observation. Second observation, eta k4 is supported on U4. Because you see, what I'm doing is that I'm taking the restriction of ck twiddle to the square, and I'm projecting. So eta k4 is supported here. Okay, it's just a projection of the measure on the square to the first coordinate, so it's supported here. Eta k is supported. Now, where is zeta k supported? Before that, let me say where IK is supported. Well, you remember IK consisted of the mass that was outside and was pushed inside by the dynamics. So to begin with, it's something that is inside U1. But this condition here says that if you are outside, the dynamics may take you inside, but not too deeply inside. This is not allowed. That's what this condition is saying. Okay, so any mass that was outside of U1 may have moved inside, but not inside U2. So IK is supported on U1 minus U2. What else? So, zeta k is supported. This part is supported outside U2, and this supported outside U3. It's supported on U1 minus U2 union U3 complement. Well, U1 minus U2 is this. U3 complement is here, outside. So the union gives me, well, in fact, it's U1 minus U3. Everything here is happening. So this is U1 minus U3. Everything here is happening inside U1. So now I can tell you where this measure is supported, where it lives. Okay? So pink corresponds to the very last term. So zeta k is outside U3, and eta k4 is inside U4. 5, 4, 3, 2, 1. So that first term, this one here, lives on this domain. This one here. See? It is far away from the diagonal. The second term is symmetric to this one, so it's clear that it lives here. No, not here. Here. Of course, again, far away from the diagonal. Okay? Let's change color. This term here. OK lives in U3. So now I have to look at U3. IK is outside U2. So I have U3 multiplied by the complement of U2. That gives me this. That's where the third term here lives. The other one, which is symmetric, lives here. It's this one. Okay. I'm just checking that the terms that I added are far away from the diagonal as I wanted, and that's how I get the constant in the statement. Okay. Now to finish this part, at least I only have to discuss this term here. And this is very different. To begin with, it's a term that is supported on U4 times U4. So it's not far away from the diagonal. It's here. And secondly, it's a negative term. I'm subtracting. Okay? Well, this is different, really. This term is smaller than that one because I'm taking the measure on a smaller domain, and I check that this factor is smaller than 1. Okay? So if you remember something that I did last time, this lemma where we wanted to remove measure from here, and we did that by putting it here and here, and then to compensate we had to subtract a little bit here, and it was crucial that what we were subtracting was less than what was there to begin with. It's exactly the same thing. I added 2 terms far away, in this case 4 terms far away from the diagonal, and then to compensate I had to subtract a little bit here, but what I'm subtracting is less than what I had there. So you just put these 2 together, you put these 2 together, and this is a positive measure. Okay. So this is harder than what I did last time for that lemma. This is more intricate, but the pictures are not so different, and the idea in the end is more or less the same. Just you have to accommodate these additional terms in the sum, and you do that by placing additional mass far away from the diagonal carefully, and then you have to compensate somehow. And the way you compensate is by subtracting from a place where you know that there is plenty of mass that you can subtract without destroying your measure. Okay. I mean, there are more details, but I think this is all I'm going to say about the proof of the proposition, because it really covers the essential points. So to finish, I want to talk about the only missing part of the proof, which is what if the ATKs are atomic? Have atoms near V. Maybe the most interesting thing that I have to say about this is that you shouldn't try to prove that this doesn't exist. It's not true. It's very easy to see that. Of course we have to have something like this. Because just think of the following situation. A1 is 2 or 3, 0, 0, 1/3, and A2 is 1/2, 0, 0, 2. Then both matrices preserve the axis, and we have stationary measures that are atomic, namely the Dirac mass on the horizontal and the Dirac mass on the vertical are stationary. Okay. And then I could do the following thing. I could take both matrices and conjugate them by some matrix close to the identity. So take matrices pk converging to the identity, and consider AK1 to be pk A1 AK minus 1, pk minus 1, and AK2 equals pk A2 pk minus 1. What I'm saying is it's a very trivial construction. You perturb the identity a little bit, take a change of coordinates very close to the identity, the change of basis, and do that change of basis to both A1 and A2 at the same time. It should be clear to you that if you do this, you are doing nothing. You're just changing the basis where the matrices are written, but you don't change anything. So this co-cycle and this co-cycle are completely equivalent by a change of coordinates. The eigenspaces are no longer vertical and horizontal. Now the eigenspaces are slightly tilted. But of course, they continue to be the same for both matrices. The stationary measures are not the same, of course. They are the stationary measures of this system moved by the change of coordinates. But that's all. Okay? So when you say that we are considering perturbations of the initial co-cycle, it could be that the perturbations are trivial, like this one. So that you're just changing coordinates. And of course, if you have that eta is atomic, then the stationary measures for this one are also atomic. Okay? This is the most intelligent thing that I have to say. Well, maybe the next sentence is still intelligent. So basically the proof to finish is to say that this is the only thing that can happen. That if the eta k's are atomic, then that's because you are doing this. And then continuity is more or less trivial because you are not doing anything. Okay, that's the idea. And that's why I said it's easy. It's not that the proof in itself is easy, but the situation is easy. You are not doing much to the dynamics. So let me try to, I think I have time to give a fair idea of what we do. To make this argument so if eta k is atomic, then, as we already proved, there exists some finite set Lk contained in PR2, which is invariant, such that Ax of Lk is Lk for almost every x. This is something that is very general. Whenever you have a stationary measure that is atomic, the way we did this, we proved even something more general in any dimension, that you can find a finite family of subspaces that this family is invariant. Subspaces either are fixed or permuted, and but so that the family remains invariant. But in this case, I make an additional claim, which is that the number of elements in Lk is at most 2. It's bigger than 1. Well, this is non-empty, finite, non-empty. So I claim that in this case, in low dimension, Lk has at most 2 elements. So either there's an element that is fixed, or there are 2 that may sometimes get twisted, may sometimes be exchanged. Now the proof of the claim is simple. We are assuming that lambda minus is smaller than lambda plus. So there are two different rates of growth. So now let us ask ourselves what matrices AX could be. What kind of matrices? And we are in 2 dimensions. In 2 dimensions, we have 4 types of matrices. Elliptic, parabolic, hyperbolic, and multiples of the identity. If we only had multiples of the multiple of the identity, for mu almost every x, then this is excluded, because if you only have multiples of the identity, of course the rates of growth are the same for the norm and the conorm. The exponents would be equal. So this is excluded. If a of x were elliptic for mu almost every x, oh yeah, remember that we already know that there exists some subspace invariant, fixed, invariant under mu almost every x. So we have a finite family that is invariant, but we also have we also have that there is one No, I'm afraid this argument is not correct. I mixed up two things. This is for mu k almost every x. Because eta k is nu k stationary. This is not correct. This is for mu almost every point, so, which has nothing to do with that. Okay, so I'm afraid that the proof of the claim is wrong, but the claim is true. So I'm going to complete assuming the claim, and then I will have to fix the proof of that claim. So, this in two dimensions we have that this finite set has at most two elements, and then there are two cases. Case one. Suppose it has only one element. Okay, suppose it is just 1 point. Then you argue as follows. At this point, so Lk consists of 1 point, one line. Then I claim, this is the second claim, I claim that the integral of phi x Lk d mu k of x is equal to lambda plus of nu k. In other words, the measure mu k times Dirac mass on Lk realizes the maximum, realizes the largest exponents. And now assume that this is true. I want to finish to give you an idea why this assume that it is true. So what this is saying is that you can calculate the largest exponent just by looking at vectors in this direction and forgetting all about the rest, which is also the case here. Lk is a kind of perturbation of the invariant subspace L that we have there. So let Z0, so up to taking a subsequence, we may assume that the Lk's converge to L0, to some L0, some subspace, and this is because projective space is compact. Okay, so Lk is such that Ax of Lk is equal Lk for mu almost every, for mu k almost every x. And then what happens is this goes to the limit, and Ax of L0 is equal to L0 for mu almost every x. So the measure mu times Dirac mass at L0 is invariant, is PF invariant. lambda plus of nu k is equal to the integral of phi x lk d mu k of x. And then mu k converges to mu. This is something that has to be checked. It's an exercise because mu k converges to nu. Lk converges to L0. So the conclusion is that this converges to the integral of phi x L0 d mu of x. And now, there are two possibilities. L0 could be our L, or it could be different. For some reason I chose different case first. If L0 is different from L, remember L was the only direction where we had slower growth than the lambda plus. So in this case, this integral is equal to lambda plus of nu, because L was the only place where we had smaller growth, and so lambda plus nu k is converging to lambda plus of nu, which was what we wanted to prove, and we assumed a week ago is not the case. So this is a contradiction. Now suppose L0 is equal to L. Then phi of x L0 is smaller than lambda plus, because on L0 the integral with respect to mu is smaller than lambda plus, because here we have smaller growth. But what does it mean smaller? I mean, we are in dimension 2. There are only two exponents. If it's not lambda plus, it has to be lambda minus. So this is equal to lambda minus. So you see, at this point, we have the following situation that is left. Lambda plus of nu k converging to lambda minus of nu k. This would be of nu. This would seem like a strange thing to happen. And it is strange, because, for example, if all the matrices that I'm considering are in SL2, this is just an observation before I kill the situation. If all the matrices are in SL2, then lambda plus of nu plus lambda minus of nu is 0, which means that lambda plus of nu is positive and lambda minus is negative. I assume that they are different. Okay. On the other hand, lambda plus of nu k plus lambda minus of nu k is also 0 for the same reason. And, of course, lambda plus of nu k is bigger or equal than lambda minus of nu k. And if the sum is 0 and one is is bigger or equal than the other one, lambda minus of nu k is bigger or equal than 0, bigger or equal than lambda minus of nu k. Okay? So, positive numbers non-negative numbers cannot converge to a negative number. This is a contradiction. Okay. So what we are left with in this situation is the possibility that the largest exponent of this new k converges to the smallest. And I'm explaining why I don't think that's possible. And I chose one example where the matrices are in SL2 to show that it's contradictory. So to finish, let me just treat the general case. In general, we prove that lambda plus of nu k plus lambda minus of nu k converges lambda plus of nu plus lambda minus of nu, the sum, and the reason is that the sum is equal to the integral of the logarithm of the determinant d mu, and this is equal to what I'm writing as part of the Oscilladets theorem, special case. Since mu k converges to mu, this log of the Jacobian converges. So we have this. We have that lambda plus of nu k is bigger or equal than lambda minus of nu k for all k. And we have that lambda plus of nu is bigger than lambda minus of nu by assumption. So you see, if the sum converges to the sum, and this lambda plus converges to lambda minus, then to compensate, lambda minus has to converge to lambda plus. Okay? So if this happens, then to compensate, lambda minus of nu k has to converge to lambda plus of nu k. In other words, the big guys of nu. In other words, if the big guys converge to the smaller limit, then the small ones would have to converge to the big limit. And that's a contradiction with these two properties. Okay. So I hope at least you feel that I didn't. It's not that the argument is trivial, but it's that at the end there's not much in the argument. And on the other hand, we cannot. This is something that exists because we have to account for the kind of trivial perturbations that I mentioned. Okay. Now we are trying to extend this continuity theorem to higher dimensions. In higher dimensions, just to finish, in higher dimensions, the problem starts with this proposition that said that exists an L. We still have that there exists some L, which is a subspace of Rd, which is invariant and expanding, and an atom. The only difference with respect to what I wrote is that in general this L is not a one-dimensional subspace. It could be. In some cases it is. But in principle
could be any subspace of Rd. So if the dimension of L is 1, then everything I said can be extended immediately. Just replace projective space. Just replace projective space by the R, the d-dimensional
projective space.
If the dimension is higher, then it is considerably more delicate, because then we cannot say that L is an element of projective space. It's not a point, so many of the things I said are false. The obvious thing would be to try to repeat the argument, but instead of projective space to use the Grassmannian manifold with the right dimension. But that doesn't work. The reason is that this is expanding if you think in terms of projective space. If you look at the dynamics in the Grassmannian manifold, it's not expanding. That the point is not expanding in the Grassmannian manifold. It's not expanding for the dynamics induced in the Grassmannian manifold. So what we did was to come up, I think we did, was to come up with an argument that goes by induction on the dimension of L, and which is not very different from this, but instead of working, for example, when dimension of L is 2, what we do to remove to dimension 1 is to look at projective space, PR3, but not at points. We look at triples of points in projective space, and we prove that in some sense L corresponds to a triple of points, which is expanding for the dynamics induced in the triple of points. So projective space doesn't work, Grassmannian doesn't work. We do something that lies somewhere in between, using various points of projective space. But that's still to be completed. Okay, that's all I wanted to say. Questions? Final questions? Very good. Teď už kanál